Welcome, my friends! Today we are going to talk about sampling. Remember that a population includes all individuals or objects that are being studied. This doesn't necessarily need to be the population of a city or a country. It could be all students at a certain school, or theoretically the population of all pigs raised on a certain feed. The population is simply the group of individuals you would like to make conclusions about. Populations are often very large, making it very difficult to collect data from every member of the population. For this reason, we often work with samples, a subset or portion of the population to study, instead of the entire population. The hope is that the sample is representative of the population. If we were able to somehow collect data from every single member of the population, we would call that a census. A census is ideal and would give us more accurate results than a sample, but it would also be extremely costly and time-consuming. The results from a sample are often good enough. Statistics would be dramatically different if we could always just collect a census. So much of statistics is based upon trying to make conclusions about a population based on a sample. In this video, we will discuss two common types of sampling, the simple random sample and the convenience sample. As we just discussed, the reason why we sample is because populations are large. A census involves gathering data from every single member of the population, which is typically impossible or very difficult. Let's say that I want to find the mean number of states visited by all Grand Valley State University students. The population is all GVSU students. Because there are over 25,000 GVSU students, I probably am not going to have the best luck getting a response from every single student. Getting a response from all students would be a census. Instead, we would probably take a sample. We would ask some, but not all, GVSU students how many states they have visited. Our hope is that our sample of GVSU students is representative of the population. This means that if the average number of states all GVSU students have visited is 10, we would hope that the average number of states that students have visited from our sample is also 10, or at least something close to 10. Let's think about a few different ways we could sample 100 GVSU students, and if each sampling technique accurately represents the entire GVSU student population. First, we could send emails to introductory statistics students until we get 100 responses. We could survey 100 students in person at the Pew campus in downtown Grand Rapids just before their night class. We could also obtain a list of all current GVSU students from the registrar's office and randomly select 100 names to send a survey to. Take a moment to pause the video and think about how representative each of these samples will be of the population. Okay. Sending emails to intro stat students would bias our results to freshmen or sophomores, since students tend to take an introductory statistics course early in their college career. If we were still asking students how many states they had visited, we might expect the lower classmen to have visited less states on average than members of the general GVSU population, so this might not be a great way to find a representative sample of all GVSU students. If we survey students right before their night class, we would probably bias the sample towards older students. There are more older students in night classes, as they might have a job to work during the day. If we asked the older students how many states they had visited, they might report a higher number than those of the average GVSU student, as they are older and have had more time in their lives to travel. If we were somehow able to obtain a list of all GVSU students from the registrar's office and select 100 names to survey, this would probably represent the population quite well. Unfortunately, it might not be possible to obtain this list, and some students still might not respond to the survey. As you can see, different sampling methods can result in a very different final result. You have to be very careful with your sampling method and make sure that the sample is conducted in a way so that the sample represents the population as well as it possibly can. Ideally, we would like to have a random sample. The gold standard of sampling is what is called the simple random sample, where every member of the population has an equal chance of being chosen at every stage of the sampling process. Oftentimes we shorten simple random sample to just saying random sample. There are many ways to get a random sample, but one method is to number all of the members of the population and use what is called a random number generator to select the individuals to sample. Scientific calculators and computer software, including Excel or R, contain functions to generate random numbers. In order for a sample to be considered random, every sample of any size must be equally likely. That means if you are sampling 30 individuals, every possible sample of size 30 must be equally likely. If you are only sampling 20 individuals, every possible sample of size 20 must be equally likely. The idea of a simple random sample can be easily misunderstood, so let's look at an example to make sure you understand what is not a simple random sample. Here is the part that is often misunderstood for a simple random sample. If each member of the population has an equal chance of being chosen, that alone is not enough for the sample to be considered random. Randomness must be applied at every stage of the sampling process, so each individual needs to be separately chosen randomly. Consider this example. Consider the students in your statistics class as the population, sitting in 4 rows of 10 students each. A coin is flipped. If it lands heads face up, the first 2 rows are sampled, and if it lands tails face up, then the last 2 rows are sampled. Is this a random sample? Well, let's ask ourselves a few questions. Does every student have an equal chance of being selected for the sample? Yes they do, but that is not enough to make this a random sample. Is it possible for students sitting in row 3 to be paired with students sitting in row 2 for your sample? No, you either choose all students in the first 2 rows or all students in the last 2 rows. Every possible sample of size 20 is not possible with this method. There are only 2 possible different samples, which makes this not a simple random sample. The point is, just because you used a random process doesn't mean that you have a random sample. To take a random sample of size 20 here, you should assign all 40 students a number and randomly generate 20 numbers from 1 to 40 to select the students. We have already talked about a simple random sample where every member of the population has an equal chance of being chosen at any stage of the sampling process. A convenient sample is another sampling method, which involves using or gathering data that is readily available or easy to obtain. Convenient samples are typically not random, and for that reason, people tend to avoid them whenever possible. But sometimes a non-random convenient sample might still be representative of the population, which is all that really matters. It all depends on the data that you are gathering from the sample. For example, if the population is all Grand Valley State University students, and the variable is height, using 10 stat to 15 students is not a random sample, but the heights will still likely be representative of all GVSU students. It isn't a big problem that our sample isn't random, because we would expect heights to be about the same in a stat 215 class as they are in the general population of all GVSU students. Okay, well, consider the same example, but now the variable of interest is class standing. Will this sample be representative of the population? Well, no. Freshmen and sophomores are overrepresented in Stat 215 classes, as it is an introductory statistics class. The convenient sample will likely produce a representative sample for the variable of height, but not for class standing. So altogether, convenient samples sometimes provide a representative sample, but it depends on the data that is being collected. Alright, the last thing to discuss is sampling error. Our goal is to have a random, unbiased sample that is representative of the population. A biased sample is a sample in which some individuals are more likely to be sampled than others. Now, here are 2 definitions that are easily confused with each other, so listen carefully. Sampling error results from the fact that the sample does not perfectly match the population, even with a well-organized random sample. It could be that your sample is very well planned and random, but the nature of randomness could lead the sample to still be unrepresentative of the population, just by chance. We call this type of error sampling error. Non-sampling error, on the other hand, results from errors in data collection, including poor study design and biased sampling methods. So if you are collecting a convenient sample that is not random, such as simply surveying intro stat students, where the population is all students at a university, you are probably going to have significant non-sampling error, as your sample is not representative of the population. The way I think about it is that sampling error is unavoidable. When you sample, you have sampling error. It's natural, even for a random sample, to not match the population exactly. On the other hand, non-sampling error is avoidable, at least to some extent. If we have a poor study design or biased sampling method, we can try to do things better next time in order to reduce the non-sampling error. The way to reduce sampling error is to simply increase the sample size. Increasing the sample size makes the sample closer in size to the population, making it more likely to be representative. Non-sampling error can be reduced by simply designing a better sample. To give you a visual representation, if you have a poorly designed, non-random sample, your sample is subject first to sampling error, because every sample is subject to sampling error. Sampling error results from the fact that your sample simply isn't the population, and therefore we can't expect the sample to perfectly match the population. A poorly designed or non-random sample would also have non-sampling error. It's like a double whammy. We already know just because we are sampling, we are likely to be a bit off. But now you have made mistakes or chosen a biased sample, creating non-sampling error in addition to the sampling error. On the other hand, in a well-designed random sample, we should only have sampling error and not non-sampling error. Sampling error will still be there because even a random sample can't be expected to perfectly match the population. But if the sample truly is random, we should have gotten rid of the non-sampling error. Most statistical methods are built assuming we only have sampling error and can reduce or eliminate non-sampling error. Finally, in a true census, there would theoretically be no error at all. If we can truly gather data from every individual from the population, there should be no error. We would know the population mean, or whatever other parameter we are trying to find, exactly. You can view increasing the sample size as a bridge, reducing sampling error down to 0, as the sample size becomes bigger and bigger, and therefore closer and closer to the size of the population. Alright, my friends, we have finished our discussion of sampling. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to subscribe and check out my other videos.